As in many fields, the amount of information in the medical field has been expanding very significantly. We now have electronic medical records. We used to have charts. Most of the information is, textual and non-structured. And electronic medical records are really not optimized to present the information in a great manner. And what we do is we kind of mimic the old chart, and we show things in reverse chronological order. And this talks about presenting that information in a better format. In 2008, these grand challenges were talked about in decision support. And decision support in medicine is how to make better decisions at the point of care. So how do you optimize my decisions at the point of care? And if you look at this list, and we've kind of prioritized the ones that are most related, is first an improved interface, summarization and prioritization of patient information. So how do you do that? How do you present it to the physician so that they can consume it well? And then how do you filter that information? I can get a lot of information in an electronic medical record. Glad to have people come on in. But if you just present that to me in a reverse chronological order, that's not a very good filter. It does give me the things that are most recent first, but it doesn't really tell me what's important about that patient. It just kind of mimics the chart. And at least in the chart, I had a feel, and I could flip through pages, and I could know where pages were. But in electronic medical record, it's reverse chronological order. And there's a lot more information that's hard to filter. So we thought that using search and these kind of search tools would help make that information more consumable by the radiologist or the physician in general. And since a lot of it is text, we thought that Solr was an interesting technology to do that. So this is just the too much information. This is from the Journal of Biomedical Informatics in 2012. And as we're all trying to do more in less time, we're much more time sensitive. And we're forced to consume very large amounts of information about that patient, lots of times in formats that are not very consumable for us. If you go to your physician now, typically, it used to be you could see the physician for half an hour or 45 minutes. Now they're kind of 15-minute intervals. And that's the way kind of medicine is going, is how to do more for less. So how does the physician consume that information in a more understandable manner? So this is a perfect example. Here's which word is out of place. Cleveland, we're both from Cleveland. It's the only city in that list, so it was pretty easy. That's usually less. If it's less than 7 pieces of information, it's pretty easy to do this. But if we look at the next one, here, which one is out of place? A lot more pieces of information here. So here, it's Paris is the one that's out of place. It's the only city that's not in North America. Doesn't have anything to do with capitalization, non-capitalization, right? But again, it's how to find the relevant information in a large set of data. And this is becoming, and we've heard that by other people at this conference, so we're just applying that to the medical realm. So this is from a 2011 article about primary care and about information overload. They put up a diagram of how to think about information overload in the medical environment. And I think first of all, you look at the amount of information, the overload, look about information scatter. So related information is in different places in the chart, so it's hard to find. And then you have a lot of information that may be unrelated to what you're doing at that specific time. And then if you look at the situational awareness and the amount of medical gymnastics you have to do just to find that information, all of a sudden you have a lot less time for what we would call eyes on the patient. So as a physician, you really want to keep your eyes on the ball, and for us the ball is the patient. So the more amount of time you can concentrate on the patient and the relevant information to that patient, the better decision you can make. But now we have a lot more information. We have our situational awareness. If it takes me a lot of mental work to find that information, I have a less capacity to make the appropriate decisions. And then there are interruptions, expertise, and the amount of time I have to make those decisions is also getting less. So this leads to, you know, potential medical errors, not making the best decision. So this is an increasingly important area in the medical arena. So I'm a radiologist. I'm typically presented with an image and some history about the patient. So this is the way it happens now. So I'm actually looking at this examination today. It happens to be a complex study of the abdomen and pelvis and chest. Which of these prior images is the one I should look at and compare with today? Well, it's presented in reverse chronological order. There's not much information. Actually, the appropriate one happens to be at the bottom of the list, right? But I have to search through a very large set of data elements to find the appropriate one, and I have to do that myself. And then there are some other key information that is not even included in this interface that I also have to go and search for. So this is a lot of extra mental gymnastics that I am doing manually while, you know, our computer systems are really just mimicking the old kind of chart and presenting information in a reverse chronological order. So the inspiration was last year in Boston. I was able to go to Leucine Revolution. I said, wow, this looks really cool. Let's try it. And what we're hoping to find out this year is we're hoping to be inspired again this week, and kind of, with all your help, is take a next advance in what we're doing. So this is, went to the conference last year, and I think this is this is really basically me at this time. I recruited Dan later in the process. He's helped out tremendously, but this was, you know, one person, and I'm a full-time radiologist, so I have other things to do. So I think this talks about the maturity of the technology. I'm not a computer scientist. I'm a radiologist. I've been in the IT area for several years, but, you know, it's kind of a secondary thing. So 28 days later, one person working on it, running on a workstation in my office that I actually put together myself from kind of scraps. We were able to index over 7 million radiology reports, de-identified those radiology reports. It was done under a kind of a research project. And within about 28 days, we were now able to do what I would call prototype searches on 6 million radiology reports, gets fairly rapid response, and do things that I could not do before. So for example, I'm looking at it for a specific fracture in a specific bone, and I'm looking for previous images to do research on. I can now do those kind of searches. So that was, I think, speaking to the level of how mature this technology is and how easy it is for even inexperienced users to do that. So this is a typical problem for me. I am a bone and joint radiologist, so if you have an MR of the knee, that's what I read. This happens to be an MR of the knee. This is the examination I'm working on right now. I have all these other images that I have to sort through. This happens to be of the chest. This happens to be of the abdomen. Here's another one of the abdomen. Actually, this one right here is also of the knee, and that's really the one I need to get to. But I shouldn't have to sort through all the rest. So this is what kind of a sample implementation that we did and kind of what we're doing. So I'm looking at a MR examination of the shoulder. So this is a typical thing that if you're an athlete or even a weekend warrior and you injure your shoulder and the x-ray is negative, you might go on to have an MR examination. So it parses out. This is the examination that I'm starting with. It does a search on the 6 million records, and it comes out with these are the most relevant ones. And you can see this one is an MR of the shoulder. This is all de-identified data, so we don't need to worry about. And just essentially a normal MR examination of the shoulder. So for our first pass, that's not bad. OK. So now what I'm doing is I am now producing a radiology report, right? We use speech recognition for all our reports. So now I'm saying there is a tear of a tendon in that shoulder. So As I'm dictating it, we reprocess the text. It does another search. Again, you can see it's an MR of the shoulder. It now has a full thickness tear of the supraspinatus tendon, which happens to be one of these tendons up here. You can see that's exactly what I'm calling in this specific report. So we're dynamically reevaluating the relevance as the report is produced. I go along further. There is actually another tear, another tendon, which is in the front of the shoulder. It kind of holds other tendons in place. There's another tendon that's actually out of place here in this shoulder. It's an MR. It's a fairly common problem with athletes. We redo the search, reevaluation, and here's the kind of the reevaluation, and this happens to be the first one. Again, we can see, excuse me, there's a full thickness supraspinatus tendon tear, which is what this patient had. There's a partial tear of the subscapularis, which is also what this patient had. And the biceps tendon is out of place. So here is a dynamic reevaluation of relevance in the medical arena as I'm actually producing a report. So we think this is becoming increasingly important in electronic medical records. It's difficult to search through all the information that you presently can find, and this will we believe that this will provide point of care information that's much more consumable by the physician. We're working in the radiology arena, and I will turn it over to Dr. Palmer to talk about the more technical aspect.
You've got the situation. We've got a radiologist in a situation doing a radiological report, and we're trying to find out whether using Solr can help us acquire the data that we need in a timely fashion. So the cases that we looked at 15 specific cases and tried to evaluate how effective the process was in coming up with information that we were looking for. So there are a lot of different kinds of searches that need to be done, but in this particular case, we're looking at, we want to see cases that are similar to this one. Not of this patient, not the patient's history, not medical reports or lab reports, but specifically images that look like this one, and we can compare the diagnosis for those cases. We wanted to make sure that these were fast. All the searches completed well within 3 seconds, so that was good. The big problem here is we want to get data. We want to get relevant data, but we really don't want to get very much data, because you can't spend a whole lot of time looking at a lot of different cases. You want to get the 1 or 2 or maybe 3 cases that are the most relevant. You want them to pop right up at the top and make sure that those are the ones that will give you the useful information. But we looked at the top 10 returns from the Solr search. By the way, we were using LucidWorks on top of it. Just that was what we were actually using. And then we wanted to count, just as a raw evaluation, how well the search was doing. Now, one problem, and I'll get into this a little bit later, is I can't tell which ones are good or not. So I can't debug this unless Dave's sitting next to me. So we had a bone and joint radiologist would look at this and say, yes, this is relevant. No, that's not relevant. So we got amazingly good performance almost right out of the box. It was a little bit startling. For all 15 cases, the average was 7.8 of the top 10 returns on the searches were relevant to the case that was being examined. And in the best performances, we got perfect. All 10 were relevant. And that's great, because we're only going to be looking at 1 or 2, maybe 3. The problem is our worst performance was there were only 2 out of 10. And as you saw in the example that Dave showed, if the 2 are down towards the bottom, you got to look, well, no, that's not what I want, that's not what I want. That's eating up time that could be used for eyes on the patient or evaluation of the medical images. We also, and this was kind of neat. As I mentioned, I'm on sabbatical from John Carroll University this semester, and I'm actually situated in Dave's outer office, and we're working on some other research together in addition to this. But I get to listen and learn by osmosis some of this neat stuff. And in a particular case, I was told about this where something very unusual happened. There was an image that came up with an odd mass in the hand that was essentially unrecognizable. And we were able to use this tool to pull up other images that looked like it by using keyword searches on the particular medical terms that were appropriate. And we were able to pull up, was it two more images? And in both cases, the diagnosis was, I have no idea what that is. But that's actually useful information. If it's the case that there were several that were like this and it was unclear, then there's a specific course of action that you take after that. So that was a good thing. And then the near and dear to my heart is our other research project. We need lots and lots of images to do other research on, and it turns out that this tool is great for that. So we can just say we want anomalous cases with strange, this kind of behavior, it just boom, go out there, and it generates an entire list. We can just grab those images and use that for our other study. So that's my little plug for my aspect of this. So here's the input flow. HL7 is a particular protocol that's used for medical records. It's text-based, it's field-based, so you can pull out relevant pieces of information and know what they are. But there's also a lot of free text in an HL7 packet, if you will. And that free text can be anything. Whatever the person creating that record wants to put in it, it's there. It can be HIPAA violations if it gets out, so you got to be careful about de-identifying it. It's free text, so you can say there is a tibular fracture in it or there is not a tibular fracture in it. And if you're searching for tibular fracture, both terms, of course, come up. So you've got to look at some of these options of saying near and no, not near. So there's a lot of issues with that. Once we pre-process that and pull the information out, because we can pick and choose the information we want, we generate our XML with the fields, and I'll show you an example of both of these in a moment. We then process them through Solr, and we've got our index and repository, which we're then doing all these searches against. So this is a typical de-identified HL7 message. You've got specific information, date, what it is, where it's found, and then there's a textual description of what's going on. And this could be a typical one. There could be some that are longer. If you're doing a bone density one for osteoporosis patients, they're usually a lot longer, and almost every term is in them, so they're constantly popping up on all the searches. Or they could be briefer. But the text here is the interpretation is where the meat of what we're looking for is. So unlike the talk I went to earlier today, where by the guy from GILT, who specifically said they eventually decided not to look at the textual information because it was misleading. That's what we have to look at, because that's where all the useful information for us is. And then this is what it looks like after we've pulled out the information and we've tagged it. So then we can actually do our searches on this. So this is where kind of the rubber hits the road, where we actually make some use out of it. Okay, and so this is then the data flow. This is kind of what Dave described earlier. You've got the radiological report being generated, and as the report continues, as he notices more things in the report gets more specific. At each point, this sends out to the pertinent information, and then it generates, it pre-processes it and then generates the query. But then we also have to do that for all the existing data out there so that we can then match them up. So we get data coming in from both directions. We get the extracted text, we process it, we generate the Solr query, and then we're given back the relevant medical records that we can then pull the images out. By the way, just so that you're totally clear on this, all the searching and all the stuff that we're doing is on the text, and they have links then to the images. So we're not doing any searches on images. So the case where we had the mass in the hand, it wasn't like we sent that out and tried to do image matching. That's a whole nother story. So the way we're going to try and fix this problem or address the problem is twofold. We've got the search, we've got good results, but sometimes we get bad results. So we want to bring the bottom up. But we also think that we can't get the radiologist completely out of the loop. There's no way I'm going to be able to tell whether I fixed the bug, right? So the other component of this is coming up with a user interface that will display the search results in a meaningful way. So there's really 4 categories of data that we're looking at. So if you would imagine the center image that the radiologist is looking at, there's a whole bunch of patient-specific information. So if they've, if we're looking at how well the tibia is healing, we might have pictures of the tibia in earlier stages of the healing process that's specific to that patient. Then we also have other information about that patient that is not necessarily the clinical notes or images. And then we also have, and this is stored in a completely separate database, so it's the information scatter, pathology reports, lab reports, et cetera. Now, all these three areas are things that we're going to be looking at down the line. What we've been looking at in particular, and you can't see it because it's cut off down here, but similar imaging diagnoses. So what we would like to do is have the image that's currently being evaluated displayed in the center, and then in decreasing relevance away from that center would be the next level of pertinence displayed. So the most pertinent image that we can determine would be displayed here, and the next ones would be here, and then it would maybe even fade. And in an example we're going to show you later is we've actually taken this and sort of formed a sphere out of it. And then I guess go to the next one. So as I said, this is where we're going to focus. We've got the main image. These are images that we've pulled up based on the Solr search that brought up the particular field, the particular data records. This is a plan that we've got for implementation of this workstation in the fall. So right now we're proving the concept using LucidWorks, and we're getting the results in the record format that we're interested in. But our next step is to then insert this into this GUI so that we can make use of the radiologist information. For example, in the case with the hand mask, when the images came up, there were 10 records that came up. I think 8 of them were unrelated. So Dave quickly went through and looked at them and said, no, 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 that's the right one. But we want to be able to do that in a way that it actually makes sense within the context of looking at the images. So we're looking at how to display images in sort of a fade-off way. And we still don't know at this point if we may have to have some textual tags associated with it or not. So here is our idea of putting it in a sphere that can rotate. We'd split the sphere into the 4 different regions of the patient information, and then the radiologist could grab it and rotate it based on what they're currently looking at. And then we would populate these images with the results from the Solr search. So if you can imagine, it would initially be looking down at the North Pole, if you will, and the globe would be split into 4 sections that would correspond to the 4 different areas that we talked about. And then when they're focusing on one of those areas, you could grab it, move it so that that takes up the full screen, and then you could click on the things that you're interested in. So this is what I'm going to dump on my students for the fall. We have a software engineering class where the students work for the entire semester on a single project, and we've got actually a really good bunch coming through this time, so this is going to land in their laps. So what are the challenges to building this prototype? We've got a time versus data challenge, which I've mentioned. The radiologist needs to be interpreting radiological images, not doing some kind of manual data searches. We've got to make that happen. The sensitivity of the queries. I mentioned that we got scary good results almost right out of the box. That was great. But so far, all our attempts to improve those results have been thwarted. And I'm almost reduced at this point to saying, well, I'll try, see if this does any better. And we're not getting those improvements yet. So anybody has any suggestions? I'll be at Stump the Chump tonight asking questions. The step where Dave looks at the images or the text and it quickly decides which ones are valuable and which ones aren't valuable, we need to either find a way of automating or semi-automating that step, or at least incorporating it into the interface in such a way that it doesn't detract from what's going on, that it supports all the machine searching that's going on behind the scenes. I've already mentioned the lack of a non-radiologist for the fitness function. That's my problem. We'll work on that. And then finally, we're using LucidWorks right now in in their GUI. We eventually want to port this over to using Solr APIs directly, and what's involved in doing that. So I already mentioned that you really only want to look at 2-3 cases max, even though we considered 10. We have to have high relevance. But the good news is that there's lots of relevant data out there. And even when we're getting very different results from the same search, depending on what kind of boost characteristics or word nearness characteristics I'm using, we're getting very different results, but they're all still reasonably good results. So I think we're the luckiest data searchers on the planet. And of course, we have almost 6 million, and for any given case, there's literally tens of thousands of images that might apply. So I mentioned the sensitivity of queries. I've been trying, by playing with different types of features, to get better results in our query. So I'm doing things with playing with the proximity. I'm boosting certain terms to see if we're getting more emphasis on the anatomical region or on the fracture or tumor or something of that. That doesn't seem to help. We've gotten ranges of results from a query with a different set of characteristics will give me the exact same 10 results, or with a slight change, it will give me absolutely none of the existing results. And there doesn't seem to be much correlation between what I'm doing in terms of changing something and whether we get results that match or that are different. Now, whether we get the same 10 or 10 new ones, they're still all pretty relevant. Most of the time, it's that bottom level that we're trying to raise up. And then I'm getting differences in literally 2 orders of magnitude in query times. It's not impinging on us yet, but if we're trying to populate that entire sphere, it's going to become a problem at some point. And we're not even sure at this point if the order of magnitude in query times has to do with the query features or some other information, maybe the network performance or who knows what. But it's like shocking. It's like you'll do a search, 30 milliseconds, 30 milliseconds, 30 milliseconds, 3,000 milliseconds. No explanation. OK, so good news, bad news. Queries are great. We're getting top 10 results, but trying to improve it has been difficult. Next. I've never had the experience in writing code where I'll try and fix a bug, I'll get a result, and then I have to walk into the next room and say, I don't say that. I say, did I fix it? So next. The fitness function is embodied in Dave's brain, and I haven't figured out a way to connect to that directly yet. I've learned a little bit by osmosis, but believe me, you don't want me doing this fitness function. So what I end up doing is I end up looking at the text and doing a very sort of rough calculation, and we're still not seeing any of the improvements. So obviously this has a big impact on debugging. So how are we going to deal with this? When I was talking at the biology and medical table at the Birds of a Feather, the only way that I see us making some progress here is that when we finally build the workstation, the prototype, when we supply the results, we're going to try a whole bunch of different types of queries, and then we're going to do click counts and calculations based on which ones seem to work the best, and adjust the frequency of which ones are used based on, I'm literally thinking of having a thumbs up, thumbs down right there on the screen that you can click right after you do your evaluation. And then the migration for the prototype. As I mentioned, we're using the manual interface right now in LucidWorks. It's been great, but we need to put this all behind the scenes of the new GUI that we're putting together. We have not done a migration like that before. As Dave said, we're both relatively new to this area. So I don't know what's going to be involved. My hope is that this isn't too bad. I've looked at the Solr API. It looks somewhat reasonable, but I haven't. What?
It's like falling off a log.
OK, good. All right. And then it's really going to be dependent on how well we can make the interface work and interface with what you're used to doing. So we're anticipating a lot of meetings this fall with, what do you think about this? No? No? OK, what about this? We'll see how that goes. Thank you very much.